Can, thank you, Gary. Yeah, we don't now see an advert for your book.
Just started the recording. Thank you.
Thanks, Sarah.
Sorry, just bear with me a minute. For some reason, it doesn't want to go in presenter view. What's going on? Just bear with me a second. Let's try that again, shall we? Okay, that's better. Okay, can you see that now?
Yeah, we can see that now. Great. Thanks, Gary.
Okay. Right. Good afternoon, everybody. As Simon says, I'm Garry Keenor. I'm professional head for electrification at Atkins, and today we're going to talk to you about pantograph gauging for minimum electrical clearances. We're going to take a slight detour first of all, but I promise you it will be. There is a point to it. We're going to have a brief canter through the history of current collection devices, and then we'll talk about what pantograph gauging actually is and why we do it. And then I'm going to talk you through what the traditional approach to doing pan gauging is, or rather was, and why that doesn't work anymore, certainly for low bridges. Then I'm going to talk you through what we should be doing instead, what we at Atkins have been doing over the last 8 months in that regard, and I'm going to show you the tool that we use and give you a bit of a demo. That part will be a little bit experimental, but we'll see how it goes, and then we'll roll over to Q&A at the end. So, current collection, let's just define what current collection is first of all. Current collection is the process of taking electric current from a fixed overhead contact system onto a vehicle. And it's easier said than done because obviously the vehicle is moving and the electrical circuit isn't. So we need some kind of sliding contact system. The first system that was developed is what you see in front of us here, is known as the trolley pole. It was first demonstrated by the aptly named Charles van der Pol in 1885, and it comprises a simple wooden or metal pole with a spring at the bottom on the roof of the vehicle and some internal elasticity. Initially, they placed a wheel on the top of the pole for current collection, but that turned out to be an incredibly bad idea. So it was fairly quickly replaced with what we now use, which is a carbon slipper which sits around the wire and slides along it. Carbon obviously being a nice soft material, which also is an excellent conductor of electricity. The trolley pole system, as they found out as they began to use it, is fine for slow speed vehicles, but once you get to about 40 miles an hour, it becomes increasingly unreliable and starts to fall off the wire at regular intervals, which is not ideal. But crucially, the other thing about the trolley pole system, which is both a hindrance and an advantage, is that it requires guidance. It's unlike all the other systems we're about to talk about. This will only follow the wire if you have a physical guidance arrangement along the wire. So what that means is that trolley pole systems effectively work. The way I characterize it is it's like putting track in the sky. So every time you come to a turnout, if it's a tram system, for instance, if you come to a turnout, or if it's a trolley bus system as you have here, if you come to simply want to change direction, you actually have to put a switch and crossing into the overhead line. So the overhead line arrangements for trolley systems are quite complex, quite heavy, and require significant maintenance and significant installation expense. So they're still widely used because they do have some key advantages. Obviously, with a trolley bus, the key advantage is the current collector doesn't have to be over the roof of the vehicle, as you see here. So that the vehicle can move around, but the current collection will still be maintained. So it's appropriate for certain uses, and it's still in use today, but it's not particularly cost effective or appropriate for guided transport. But nevertheless, it was the first system, and crucially to the story of current collection, de Pol was smart enough to patent his system. The next device that we see coming into use shortly after the trolley pole is what's known as the bow collector. The bow collector was developed by Walter Reichel, who worked for Siemens in 1889, specifically to avoid infringing on de Paule's patent for the trolley pole. And the crucial difference here is that this is the first device that removes the need for the current collector to follow the wire. So basically, it is a simple spring pushing up on a lever, to which the end of which is attached a steel collector plate. And crucially, the steel collector plate is wide enough to cater for the full range of cross-track travel of the wire across the current collector. So that means that the device no longer has to follow the wire. And this requirement is going to come later on when we talk about, it's going to become important when we talk about gauging later on. There is one major downside of this arrangement though, which is that there's only one wire height at which the collector plate is actually parallel to the surface of the wire. Above and below that height, the collector plate is going to strike an angle on the surface of the wire, which is going to lead to increased wear and tear on the wire. So it's not really suited to overhead line system with a widely varying wire height. And that basically describes every overhead electrified railway except for purpose-built high-speed lines. So although it was used on some early systems, and the one on the left is the old London to Brighton line, which had AC overhead line in the early years of the 20th century, it quickly fell out of favour because it wasn't very frankly wasn't very good, particularly at higher speeds. And speed is a consistent theme through this talk. The faster you want to go, the more crucial it is to get this interface right. Shortly after that, we see effectively the first device that can be described as a modern pantograph. And that was invented by John Q. Brown, who used it on the East Bay Railway in San Francisco as early as 1903. And it's the Diamond Pantograph. And unlike the bow collector, the diamond linkage means that the collector head is always parallel to the surface of the wire, regardless of the wire height. So that makes it suitable for mainline operation on railways and for higher speeds. And this was adopted in use throughout the world. It was used in the UK right up to around about 1980. And it was used on many of the early Shinkansen high-speed routes. So it is effectively the first modern pantograph capable of operating competently at high speeds. The next development in pantographs comes in 1955 when Louis Faverly in France develops the single arm pantograph. What Faverly did was to replace the diamond linkage with a parallel lever linkage using a single arm. So the level collector strip is maintained by these parallel linkages, but crucially it reduces the number of joints, which means it reduces the amount of friction, which means that the pantograph becomes more responsive to changes in force at the interface, which is really crucial. Low hysteresis is something you really want in a pantograph. It also helps to reduce aerodynamic turbulence. At high speeds, the main factor that influences contact force and basically pantograph performance is the amount of aerodynamic turbulence and drag that's occurring over the pantograph as it moves through the air. In 1973, Brecknell Willis, who are a UK pantograph manufacturer, they're now owned by Wabtec. Back then, they were an independent company, and they are the dominant pantograph manufacturer in the UK to this day. In 1973, they took the single arm design and developed it further, based on a concept by Bob Whiteley. What Brecknell Willis did was to replace the external bar linkage with a system that's entirely contained within the upper and lower arms, using a set of lifting chains to lift the upper arm. So I'm going to show you now, hopefully, if the video comes through on Teams. And Simon, if you can maybe just give me a quick heads up on whether it's working well or not. This is what we're going to see here is Steve Cullingford, who is Brecknell Willis's technical guru, demonstrating the lifting of a pantograph in their factory using a temporary air supply.
Yeah, the video's working, Gary.
Excellent. Okay, so Steve's putting air in the system now, and it's rising. So I'll just pause the video there and just explain what's going on, because it's quite hard to see what's going on. So essentially, this is the lower arm, this is the upper arm, this is the raising cylinder. So this is a pneumatic cylinder which pulls on a lever down here and pulls the lower arm upwards. Within the lower arm is this thing here called, which Brecknell Willis, for reasons best known to themselves, call the fourth bar. Don't know where the other three went, but that's the fourth bar. And then attached to the fourth bar is a set of lifting chains, which you see here. And the lifting chains pull round this cam and attached to these lifting bolts here, which is fixed to the upper arm. So these lifting chains force, as the fourth bar is pulled in, the lifting chains are pulled backwards, and that forces the upper arm to rise. While this is all going on, there's another arrangement here. You see this V-shaped arrangement which sits in a slot and connects to an internal bar which runs all the way up the upper arm to a linkage here, and it's that maintains the parallel head. So let me just run that again. What we'll do is we'll just repeat the video so you can watch it and hopefully see what's going on. Let's run that again. So watch as the lower arm rises, you'll see the fourth bar pulled back into the lower arm. There it goes, gets pulled in, lifting chains pull round the cam, upper arm is forced to rise, and then the head linkage keeps it parallel. So very clever design. The advantage is that it reduces the aerodynamic drag even further. The disadvantage is that lifting chain arranges. If you think about this as a lever, for those of you mechanical engineers, you'll be looking at this probably wincing, thinking the mechanical disadvantage on this is pretty severe, and you'd be absolutely right. The forces on those lifting bolts are very large, and they occasionally give trouble. But on the other hand, when something goes wrong with overhead line, and if something has to break, you want the pantograph to break. It's always better for the pantograph to break than for the overhead line to break, because replacing a pantograph is a fairly straightforward job in a depot, whereas replacing a mile of overhead line is anything but straightforward. So that's the Brecknell Willis single arm pantograph. So now we're going to talk about a little bit about suspension, which becomes very important to the topic we're discussing today. Now, at low speeds, a certain amount of suspension is provided by the lifting mechanism itself, the pneumatic cylinder at the base of the pan. And we're going to call that the primary suspension from now on. And for low speeds, primary suspension is enough to maintain good contact. So if you look at a tram pantograph, if you're ever out in Birmingham or Leeds or Sheffield, Nottingham, places like that with a tram, have a look on the tram, and you're not going to see anything on the tram head in terms of suspension. It's just purely done at the base of the pantograph. But as you start to increase speed, the problem arises of unsprung mass. So essentially, unsprung mass, so those of you who are kind of familiar with vehicle dynamics or maybe car mechanics, unsprung mass is any mass that's in contact with the moving interface. So in your car, the unsprung mass is basically the wheels and the axle and anything below the suspension. In the pantograph, it's anything above the suspension. If you only have primary suspension on a pantograph, then basically the entire pantograph linkage is unsprung mass. An unsprung mass means high inertia, and high inertia means inability to react quickly to changes in circumstances. So if you try to go fast with a pantograph with only primary suspension, what you will see is loss of contact. You'll see the pantograph bouncing along the wire, which is extremely bad news. So for higher speeds, what we do, just as with a vehicle bogie on a train, we would add secondary suspension. And typically what we do with a pantograph is we add the secondary suspension between the upper arm and the carbon interface with the contact wire. So on this pantograph, the primary suspension is down here at the base, and the secondary suspension is these springs here and here at either end of the head. So by doing that, it means that the unsprung mass is now just the mass of the head, and that's typically no more than about 10 kilograms. So that's kind of a brief potted history. I could do a whole talk about pantograph design, but we're not going to do that today. That's how pantographs work currently on the railway today. So now let's talk a bit about gauging. Well, first of all, and I apologise, I'm always conscious when doing PWI talks these days that probably talking to a mixed audience, probably some track engineers on the call, probably hopefully some overhead line engineers as well. So for those of you who aren't familiar with gauging, I'm not going to read this out, but essentially gauging is the process by which you make sure that nothing on the train is going to come into contact with anything on the infrastructure. So obviously for those of you with a track background, you'll be well used to talking about gauging of vehicles. Well, a pantograph is part of a vehicle, so we also need to gauge the pantograph. However, in one crucial aspect, the pantograph problem is different to the vehicle gauging problem and more onerous. And that's because unlike rail vehicles, pantographs are energized at voltages up to 25,000 volts. So what that means is it's not sufficient for them just to be mechanically clear of the infrastructure. It's worth bearing in mind that the only thing that prevents electric current flowing from the pantograph to something else, say a bridge or a canopy or somewhere else you don't want it to flow, is some sort of insulating medium. And for pantographs, that insulating medium is air. And what that means is we have to maintain minimum air gap electrical clearances between the pantograph and anything that isn't live to prevent flashover occurring. Now, to give you some context, and this number is quite, important to the rest of the talk, so just kind of put this number in the back of your mind. But for normal 25 kV systems, including overvoltage conditions, we would be looking for a 200 millimeter air gap between the pantograph and anything that isn't live. So 200 millimeters, 8 inches. And we've got to maintain this air gap at bridges, including flat deck bridges, arch bridges, but not just that, station canopies, signal heads, the earthed parts of overhead line structures, anything that's earthed, anything that's not live, we've got to maintain that clearance. So what that means is, as we're doing an overhead line design through these items of infrastructure, we have to develop a swept envelope for the pantograph head itself, and then prove to everybody that everything is clear of that envelope plus the electrical clearance that we're looking for. So since the dawn of electrification, people like me and Simon have been doing pan gauging, and using what is actually a very simple, quite crude process. So what I'm going to do is try and, with the aid of a little animation, try and walk you through what that process is. I've deliberately simplified this. Those of you who have done this process in the past will be saying, but what about this factor and that factor and the other? I've rolled up all the parameters and all the tolerances into basically one simple process, just for simplicity's sake. So what do? Well, we start by working out where the track is. We then place a pantograph profile. So this is the physical shape of the static head. We place that profile in the plane of the track. We then raise it, and we raise it to a height that's equal to the contact wire height plus the uplift. So that's the vertical upward movement of the wire under the force of the pan, plus a bunch of tolerances, track tolerances, OLE tolerances, and various other factors to give us our total height that the pan will operate through. And that height is known, you'll see this talked about in standards, as the contact plane. So that's the plane through which the pantograph will move as the train moves. Now that's not enough on its own, because trains have other modes of movement. Specifically, they move left and right on the suspension, so we have to account for that as well. And the way that we do that, again, is very crude. We have a set of sway values that we operate to, and those sway values have been predefined in a group standard, GMRT 2173, for those of you who are interested. And that dictates sway value based on the wire height, because obviously the higher the pantograph is, the more the vehicle is going to magnify the movement of the pantograph. So it's based on wire height. It's also based on wind speed in the area, and it's also based on cant deficiency, because obviously at high cant deficiencies you are going to see more slump in the bogies of the vehicle and the suspension. So what we do then is we translate the pantograph right and left. Now the astute people in the audience will be probably thinking, well, that's not how it actually works, and you'd be absolutely right. It does not sway in the plane of the pantograph in that way. It actually rotates. However, we're trying to gauge for multiple different vehicles, different centers of mass, different bogie systems. So it's very, very difficult to do that. So we deliberately simplify it. And that's a fairly consistent theme through this talk, is that our gauging approach has been very crude in the past. It's getting less crude, but it remains a fairly crude simplification. But it does the job. It does, it's good enough for the purpose. We then apply a electrical clearance envelope to the resulting gauge, and then we have to check that everything that comes near to that pantograph is outside of that red line. And that's how we've been doing pantograph gauging for the last 100 years, I'd say. And usually in most OLE teams, there's one or two people who are quite good at this, and they'll develop the gauges for the project, and then everyone else just uses them. And that tends to be how it works. So now we get onto the real meat of the talk. Why this approach is no longer valid, unfortunately. The bad news for anyone who does this on the call is that change is coming your way, and you should grasp it, because not grasping it is going to lead to some bad decision making and some potentially bad outcomes for you at bridges. And there are two distinct changes in the industry in recent years that have invalidated the approach that you see on the left, which is a conventional gauging approach. The first is that we're using much smaller air gaps. We're in many cases, we're no longer using that 200mm air gap. And the reason for that is a thing called a set of techniques called voltage control clearances. Now, the subject of today's talk is not to go through what voltage control clearances are. There have been, I believe we've had talks before. I know PWI have posted talks. I'm sure if you go on our YouTube channel, you'll be able to find Richard Stainton talking about VCC. So I'm not going to go through that today. All you need to know, if you're not familiar with VCC for the purposes of this talk, is that VCC allows you to use air gaps as low as 20 or 25mm instead of 200mm. And that means we can have much lower, significantly lower overbridges that we can get through. So to give you an idea, the gauge on the left is using pure air gap clearances to maintain the insulation strength, no VCC. And on the right is the exact same bridge, but this time we're using VCC. And you can see how much smaller the envelope is. And we've taken effectively the minimum soffit height of this bridge down from 4889 to 4709, simply by applying voltage control clearances. So the thing is, if you're using a 200mm air gap clearance, if your pan gauge isn't quite right, it doesn't really matter. If you're a few millimeters adrift, nothing bad's going to happen. It will be okay generally. So in the past, we haven't worried too much about making that pan gauge process more accurate. But if you're designing things and engineering things to 25mm tolerance, and your pan gauge isn't quite the right shape, then you've got a problem, because you actually haven't got 25mm of clearance, you've got something less. And that's the first reason why the traditional approach doesn't work at the moment. So just to give you an idea, if you look at on the left-hand side, the way to read this graph is that the red and orange lines are the electrical clearance envelope. That's the line that everything has to be outside. The light blue line, the light blue dashed line, is the actual pantograph swept envelope. You can see that's quite a generous, there's 200mm clearance between the two. On the right, look at the same lines, the orange and red, and then the light blue, and you see how close together they are. You can see how much less wriggle room there is. But this on its own wouldn't be sufficient to invalidate the traditional approach. However, the second change that came in was the arrival of the floating head pantograph in the UK. So we're going to talk a little bit about that now. And in order to show you why this approach is no longer suitable and what floating head pantographs are, first of all, I want to show you what a traditional pantograph looks like in actual operation. So this is a typical fixed frame pantograph. This is the Brecknell-Willis. We're back to the pan that we saw in the video earlier. This is the Brecknell-Willis high-speed pantograph. And until 2010, this was the state of the art in the UK. Now, the thing that you need to understand for the purposes of this is that the way that the secondary suspension works on this pantograph head is unlike the one that we saw previously, is that this arm here rotates in the pitch axis, and that rotation is resisted by an anti-torsion bar which sits just here. Right. So the secondary suspension is this entire head rotating in the pitch direction and being resisted by this bar. So what we're going to do now is on the next slide, hopefully the video will stay with us. So what we're going to see now is some pantograph footage, high speed. This is East Coast Main Line, 125 miles an hour. And this is a high speed pantograph in operation. This is on a short loop, so I'm just going to talk for a few seconds just to kind of describe what's happening here. So obviously you can see the upper arm going up and down with wire height. So that's dealing with the kind of low frequency changes in the contact wire position. But all of those small changes in height and contact force at the head are being managed by the secondary suspension. And you can see that very characteristic jiggling action as the whole head rotates backwards and forwards in the pitch axis. And that's absorbing the changes in contact force, or attempting to absorb the changes in contact force. And the unsprung mass of this head is around 10 kilograms. The second thing I want you to pay attention to is those funny looking assemblies on the end of the pantograph. So those are known as the horns, and they're there just in case. Basically, they're there to prevent the contact wire from ever getting underneath the pantograph. So if the contact wire goes out of geometry for some reason and it approaches the end of the pantograph, it's there to stop that happening and to keep the contact wire on the pan head. That's going to become very important in a minute. But crucially, looking at this footage, you can see that the head shape is fixed. The shape of the head itself is not changing. It's going up and down, it's jiggling backwards and forwards, but it's not changing shape. So for this type of head, the traditional approach is still valid. However, this pantograph predates the introduction of the TSIs, the Technical Standards for Interoperability, which have now been superseded by the National Technical Specification Notices, the NTSN. But what the TSIs require us to do is to maintain the contact force measured at the interface between the pantograph and the contact wire within strict limits, broadly speaking between 0 newtons and 300 newtons. The rules aren't quite that simple, but that gives you a rough feel. So quite a strict band that we need to stay within. So the TSIs come in and they impose some contact force limits on us. Those, we had contact force limits before the TSIs. Maybe they weren't quite as strictly enforced, but we still had them. But the other thing that happens is we start deciding as an industry to run EMUs, electric multiple units, in multiple with multiple pans raised at high speeds. So we start running 12-car EMUs. So that's 3 4-car EMUs coupled together at high speeds, 110 miles an hour with 3 pans raised. And those pans are only 80 meters apart. So what happens in that scenario when you start running 3 pans up at high speed is that each pan sets up a standing wave in the wire, and those standing waves start interfering with each other. Then that interference means that contact forces go up and go down. The extremes of contact force start to rise. your mean contact force might stay the same, or it might rise a bit, but your minimum and maximum contact forces start to go down and up, and you start to fail to comply with the TSIs. So what do we do about that? Well, the industry went to Brecknell Willis and said, please help. And Brecknell Willis, in response to that request, developed a floating head pantograph. They weren't the first to do this. There are plenty of floating head pantographs operating in Europe, but this is the first time where they were used on the GB mainline. And the way a floating head pantograph works is it further reduces the unsprung mass. So how does it do that? Well, it takes the horns out of the unsprung mass and puts them below the spring. So you see here, this is the HSX pantograph. This is a floating head pantograph. And what you see here is there's a spring arrangement on this one is slightly different. It's a lateral spring, but the horns themselves, instead of being a closed frame, they're now an open frame horn, and they're fixed to the actual upper arm. So they're no longer above the spring, they're now below the spring, and the only thing that's above the spring is the carbon head itself that you see here. And that simple change in the design reduced the unsprung mass by about 3 kilograms, which is quite significant in terms of pantograph performance, and it significantly improves dynamic performance. So what we're going to do now is we're going to have a look at one of these pantographs in action. And hopefully what you can see is a very different mode of behavior from the one we saw before. Instead of rolling in the pitch axis, it's now moving in the across track axis, in the roll axis. And the springs are reacting to two things. One is the actual contact force itself, but the other thing is, because the springs are at each end of the pan, it's also reacting to the position of the contact wire. As the contact wire moves to the left hand end moves down and the right hand end moves up, and vice versa. So what that means now is that, unlike the previous pantograph head, this head hasn't got a fixed shape anymore. It is changing shape moment to moment in response to the contact wire position and contact force. So just very quickly, I'll show you the two pans side by side, just so you can see the difference. And then we'll go into what that means for pan gauging and what we're doing about it. Okay, so as before, we can now see that we've got a pantograph that doesn't have a fixed shape, and therefore applying a fixed gauge when you've got very small clearances isn't a valid approach. And the reason for that is a thing called encroachment. Essentially, what happens is, as you push down on one end of the pan head, the other end, the spring if the contact wire is on the right hand. So what we see here is a setup with the contact wire with a 250 right hand stagger. So the contact wire here is on the right. As it pushes down on the right hand side of the head, particularly when it's fully swayed to the left hand end of the head, the spring is uncompressed, and the right hand spring is almost fully compressed. So that means the left hand end of the pantograph is higher than the right hand end. Crucially, it's higher than the contact plane. So the live parts of the pantograph are now intruding above the contact plane. That doesn't happen with a fixed frame pantograph. So we call that intrusion above the contact plane. We call that encroachment. You're going to see that word used a lot in standards. So for those of you on the call who are lead designers, get used to hearing about encroachment. It's been in standards for the last 7 years, and I get this distinct sense that OLE designers still aren't fully on board with this idea. But it's simply the intrusion of the pantograph above the plane of the contact wire. So what I'm going to do is I'm going to show you. So this diagram here is a fixed frame pantograph with a contact wire stagger of 250 millimeters to the right. So what you can see here is a little bit of encroachment because the contact wire is starting to roll down the curved portion of the head, but only about 10 millimeters of encroachment here. So if you've got 200 millimeters of clearance, you're probably not going to bother trying to calculate encroachment. There's no real value in doing that. Now let's look at the same scenario with a floating head pantograph. So this is exactly the same scenario, but we've replaced a fixed frame pantograph with one with a floating head. The solid blue line is the head before the encroachment is applied, and the dashed blue line is the head after encroachment is applied. And the difference here is 62 millimeters. So even if you're applying a 200, even if you're looking for a 200 millimeter electrical clearance, and if you use the traditional approach, you're actually over-reporting the clearance by 62 millimeters. That's not good. Any OLE engineer will know that's not good. Clients aren't going to be happy with that. They're expecting to see 200 millimeters to the actual pantograph. But if you look at VCC, if you start looking at VCC clearances where we haven't got 200 millimeters, we might only have to the pantograph, we could have as little as 80 millimeters. And you've got 62 millimeters of encroachment, you've actually only got 80 millimeters of electrical clearance, and that's not going to be remotely acceptable to anybody. And that's why we can no longer afford to ignore floating head pantographs and encroachment. Clearly, it's not for everywhere. If you've got open root pan gauges for open root cross sections, the traditional approach is still valid. But wherever you've got tight clearances and or VCC, you need to be calculating encroachment. So now I'm going to talk about so this is the problem, and this problem's really arisen over the last 18 months really, because VCC is beginning to become business as usual. It's beginning to become part of the day-to-day approach to electrification. Atkins are designing the middle and mainline electrification, and we're using VCC routinely. We're going to have about 50 bridges with VCC on them. Transpennine route upgrade, they're using VCC as well. Schemes in Scotland are using VCC. It's becoming the norm. So as Atkins, we felt that we had to respond to this problem. So what we did is develop an Excel-based tool that we've called PanGen, and what it does is generate a site-specific absolute pan gauge that includes encroachment. It's based on the mechanical data in a document that Nebrail have published called EPTAN 002. Any of you in the overhead line space hopefully are familiar with EPTAN 002. If not, please go and ask your DPE or PE for a copy, because it's probably going to become a standard very shortly. It's not currently a standard, but it is going to be in the future. And it defines an approach to gauging bridges using VCC. Crucially, it also contains all the information about the pan heads themselves that you need to develop a tool that considers encroachment. It gives you the shape of the head as coordinates, and it gives you the mechanical response behavior of the heads as well. So we developed an Excel-based tool based on that new information. It allows you to develop a site-specific gauge. It allows you to play around with parameters, see what the outcome looks like, and then when you're happy with it, it allows you to export the resulting gauge into our in-house design tool, which we call Polcat. So it allows you to import it into that tool and then use it in your overhead line design. The approach we've taken for this tool it doesn't fully reflect reality. It's still basically a static absolute approach to the pantograph envelope. We make an assumption about contact force to allow it to be a constant value, which, as you've probably seen from the footage, contact force is anything but constant. But we needed to make an assumption to be able to develop gauging. So we made some assumptions about contact force that allows us to do that. So it doesn't fully reflect reality, but it's a significant improvement on the traditional approach. And I don't think within Atkins, we're certainly not done with this story yet. We're not done developing this. We're already discussing what the next steps are for this tool. It doesn't do It will allow you to develop a traditional pan gauge. If you want a boring bog standard pan gauge for open route, it'll quite happily do that for you. What it won't do is it won't do dynamic gauging yet. That's something we're discussing, and it doesn't do probabilistic analysis. So for any of you who've seen any of D-Gauge's talks, that's probabilistic gauging. This doesn't do that. This is still absolute gauging. Okay, so that's the end of my slides. What I'm going to do now, assuming that the technology continues to play nice, is I'm going to do in fact, what I'm going to do is I'll just switch the screen share now. So just bear with me. I'm going to switch that off and then share. No, wrong one. Share that screen. Right. Okay. Simon, have we got a nice spreadsheet in front of you?
We've got a very lovely spreadsheet with lots of colours on.
Great. Okay. So this is the boring half of the tool. This is where we put all their input parameters in. And for those of you who've done traditional pan gauging, this probably looks relatively familiar. This is essentially us over here building up all of the parameters that lead to us determining what the height of the contact plane is. So we have lots of tolerance. We have survey tolerance, track tolerances, various track tolerances, the load gauge itself, the height of the vehicle. We have some additional allowances that we have for things that I won't bore you with to do with dynamic movement and extra allowance for steam trains. We have OLE construction tolerance. We have a clearance between the vehicle and the wire. We have some additional OLE parameters to do with OLE geometry. And that basically gives us a minimum permissible contact wire height under all conditions. The user then decides what wire height they actually want to select, because we might not want to go in at the minimum wire height, we might want something else. And then it develops continues to develop the heights all the way up to and including the actual soffit height itself. So we can see with this, with the parameters I picked here at the moment, my minimum contact wire, my minimum soffit height for a bridge would be just under 4.9 meters. So you develop your parameters here. We also have some parameters over here to do with lateral tolerances. So we also have a lateral track tolerance, which is obviously something that the track engineer needs to allow track to be maintained. We have some other lateral tolerances. Crucially here, and we'll play with these numbers shortly because these are the actual electrical clearances that we want to use. At the moment, these are non-VCC electrical clearances. So this is if you want a traditional pan gauge without VCC, these are the sorts of numbers you're typically going to use. In fact, I'd probably add one more, which is to change the static clearance to 270 millimeters. And there's also a further thing down here that allows us to calculate sway. That's just doing a sway calculation in accordance with the group standard. So we've got 213 millimeters of sway at this particular location. And then we have some other stuff to do with carbon wear that I'm not going to bore you with. Crucially, we have to select a contact force. So this is probably the biggest weakness in this approach at the moment, is picking a static contact force. Simon will tell us all about how contact force actually works and what test trains show us, and what they show us is contact force that varies anywhere between 0 and 300 newtons moment to moment. So we have to make an assumption there. So at the moment we're using 150. It's not ideal, but it's better than the previous approach, which basically ignored contact force altogether. I'm not going to bore you with the rest of it. So those are the inputs. Once we've got the inputs, we come over here, which is the more interesting. Let me just get rid of this. The more interesting part of it. So what this gives you then is the resulting pantograph gauge. The view on the right is the accurate view with a 1-to-1 scale. So we have the train vehicle in grey. We have we have the static pantograph here. Then we have the uplifted and swayed pantographs here. And then finally we have the red and orange lines, which are the actual electrical clearance gauges. Over on the left, we have the same, it's exactly the same view, but it's exaggerated in the y-axis just to allow you to see a bit better what's going on. I should also add this funny looking thing here is the bridge arm. This is a fitted bridge. If we have a free running, we can also pick a free running bridge if we want, in which case the bridge arm will disappear. So there is a free running version. I'm going to leave it fitted because I don't want to confuse everybody with static clearances and top hats and all that sort of stuff. So this is a traditional. I mean, this at the moment. Let's just see what pantograph have I picked here. So this is a fixed. This is now a fixed frame traditional pantograph gauge. So what I'm going to do is I'll just zoom out a little bit because laptop screen doesn't really allow me to squeeze more in. What I'm going to do now, this is at the moment we have a 0 stag. You see the contact wire here is directly over the track center line. So what we're going to do now is we're going to start changing the stagger and seeing what the effect is on the pan gauge. Now remember, this is a fixed frame pantograph at the moment. So what you see is as we move the stagger, essentially nothing changes. Obviously the bridge arm itself moves, but nothing much else changes. The pan head itself, it's the left-hand swayed pan is lifting slightly, but that's purely down to the fact that the wire is beginning to move down the head and towards the horns, which frankly is something that you don't want. So in reality, we would never design a bridge arm to be out at a 300 stagger, for instance, because we're getting into the danger zone, and that's not a good idea at bridges. So we would probably stop about 200. So you can see there that, basically the fixed frame pantograph doesn't really change between 0 and 200 stagger, which is the area that we're interested in. And if I go the other way, it's exactly the same. Let me just go over to 200 in the other way, which, I mean, we wouldn't normally set up a bridge arm like this, but let's just pretend that we did. Again, the shape of the pan hasn't really changed. So let's reset that back to 0. Now I'm going to switch. Now I'm going to bring in a floating head pantograph so you can see the difference. So now we've got 2 pan gauges overlaid, but we're still at 0 stagger. And you can see that at 0 stagger, there's not really much difference. There's very little difference here. There is a bit of a difference here between the fixed head, which is here, and the floating head. At the moment, we've got, and this tells you how much encroachment, we've got 19 millimeters of encroachment. And that's purely down to the fact that when the floating head pantograph is swayed to the left, as far as the pantograph is concerned, it's seeing a right-hand stagger. The wire's pushing down on the right-hand side of the pan, so the left-hand side is moving up by 19, but it's only 19 millimeters. So at the moment, we've got 200 millimeters of clearance. Well, we said we had 200 millimeters clearance. We've actually got about 180 with the floating head pantograph. So it's not great, but it's not disastrous. And chances are nothing bad's going to happen when that floating head pantograph goes through that bridge with 180 millimeters of clearance. Probably going to be okay. And that's basically why, as an industry, I think we've been, to some extent, ignoring the problem of encroachment up to now. But now let me start introducing some stagger, and let's see what happens to the difference between the 2 pantographs. So I'm going to take it over to 200 right now. So now let's have a look at the difference. So now you can see the fixed head here and the floating head up here. We've now got 60 millimeters of encroachment. So that means that this red line is 60 millimeters higher than the traditional fixed gauge red line. 60 millimeters on a 200 millimeter clearance. That's not good. We're now effectively, we would be reporting a 200 mil clearance, but only actually having 140. So that's not good. So what I'm going to do now is go to the next step, which is to bring in voltage control clearances and then look at what we've got going on. So I'll reset it back to 0. Sorry, reset that back to 0. So you're gonna have to bear with me here because I have to change some of the inputs here. So let me just see, what do I want to change? So I'm going to change the clearances first. So we want fixed live parts to the train. We can go as low as 75. This is all in the EPTAN, by the way, if you haven't already read it. Fixed live parts to the bridge, we can go as low as 20, as long as it's not a steel bridge. Live parts of Pandagraph to the bridge, we can go as low as 80, and the horn clearance, we can also go as low as 80. And for VCC, we're not interested in static clearance, so we'll just set that to 0. Right, the only other thing I need to change, that's at VCC, good, that's all good. The other thing I need to do is change, I'm going to go down to my minimum allowable wire height, which is now 4181 millimeters. Right, hopefully I've done everything I need to. Actually, there's one other thing I'm going to change, which is I'm going to change that to 44 millimeters of uplift. Okay, I think everything else is what I want. I've now got a minimum soffit height of only 4, we're well under 4.4 meters now, from 4.9. Some of that was, to be fair, was me changing the uplift allowance, but it's still a significant saving. So now let's go back to the chart and see what we've got. Now immediately you can see we've dropped so much that we've actually fallen off the edge of the graph. So let me just recenter the graph. Let me get rid of, tell you what, I'll make a couple of changes here as well to make it a bit more screen space. So now let's have a look at, I mean, immediately just look at the distance now between the blue lines and the red line over here. Let me zoom in a bit on that to help you. These are very small clearances now. There is very little room for error now with VCC, even smaller with the bridge arm, but we're not going to get into that because that's not really related to pantograph gauging. But we've now got only 80 millimeters between the head and the edge of the clearance line. So we could have a bridge, we could have a portion of an arch bridge just outside this red line. But now let's have a look over here and have a look at the exaggerated view. So we can now see that we've got 80 millimeters of clearance here, but we've got, at the moment, remember we reset the stagger to 0, only 17 millimeters of encroachment. So if we were using traditional gauging, we'd be reporting an 80 mil clearance, but actually only having a 63 millimeter clearance, which is not good. VCC is a minimum viable approach. The whole point of minimum viable is you can't cross the line. You can't go beyond it. So if you do go beyond it, you're potentially in trouble. You're potentially going to get a flashover. So I'm going to do now is zoom back out and start applying some stagger, and then we'll see what happens to that. So let's start applying stagger again. Let's take us out to 200 millimeters again. And now let's have a look at our exaggerated view. So what we can see now, we've got how much encroachment we've got. We're back up, we've got 50 millimeters of encroachment now on an 80 millimeter clearance. So if we weren't allowing for encroachment, we would actually only have a 30 millimeter electrical clearance, which would not be remotely acceptable. And you can see the difference here between the fixed head and the floating head. I'll just zoom out again to allow myself to switch. I'm going to switch the fixed head on and off. I haven't really thought this through, have I? I'll tell you what I'll do. I'm going to move this. Just going to move this upwards for a moment. Right, so I switch the floating head on and off. Right, so there's your fixed head. That's what your fixed head looks like. Very little encroachment going on there. Now we add the floating head, and we've got 60 or 50 millimeters of encroachment. So I'm going to wrap up now. I'm going to take us back to, bear with me, I'm going to take us back to the PowerPoint. I'm going to summarize and then we'll go to Q&A. So in summary, our traditional pan gauging approaches, which have been valid for basically a century or more, are no longer viable for low clearance situations. They're still viable for open route. If you're doing open route cross sections with non-VCC clearances, if you're doing just applying 1210 clearances, you can continue using a traditional approach and you'll generally be okay. You should probably still be looking at encroachment because, as you can see, it actually reduces the clearances you think you have, but you could get away with it. But if you're at low overbridges, whether they're VCC or not, I would argue at low overbridges, tight canopies, low signal gantries, we should now be applying encroachment to the pan gauge that we're developing. And so that means that overhead line designers need new tools that account for this. Now, as you can see, we've developed a tool. It's not perfect yet. In the fullness of time, we want to integrate it more with our Polecat suite. We would like to make it fully dynamic. We're in discussions with TRIS about potentially incorporating it into their dynamic simulation tool, because that would allow us to get real-time contact force and have a real-time changing pantograph. But there's no doubt in our minds that this is a significant improvement on the traditional approach and has essentially de-risked all of our projects where we're using VCC clearances. Without it, we would be in a sticky spot because we would be under-reporting electrical clearance, and that's for an overhead line engineer, that's never something you want to be doing. So that concludes my talk. Simon, happy to open it up to Q&A now.
Thank you, Gary. It looks like we've got another section of your book, or the next section of your book in the next draft coming shortly on pan gauging. So thank you.
Yeah, definitely.
And also future, so thank you for volunteering for doing a Pandagraph talk as well, probably in the next couple of years. Thank you for that. So I can see there's a couple of questions coming through in the chat. So I'll start off with one of my own before calling through that. If you want to raise your hand as well, if you've got any live questions that you'd like to ask Gary, please do. So I'm just presuming, Gary, going ahead with the traditional method, actually we're not seeing some of the savings that we could see, and potentially having to do some reconstructions and that, so therefore electrification is not as viable as it could be.
That's right? Exactly it. That's exactly, and that's why if you're in, if you work in OLE design, you need to get on board with this new approach, because if you might think, well, my existing tool well, first of all, it's not conservative. That's the first problem. So you're going to be underreporting clearances in certain scenarios, particularly in medium or high stagger scenarios. You will underreport clearances. But if you try and apply it, if you try and apply it on VCC in a VCC situation, you're actually going to be heading in the other direction. You're not going to be costing the industry more, but you are going to be painting a more optimistic picture than the one that actually exists. At some scenarios, you'll get away with it. If it's a flat deck bridge, for instance, it tends to be the bridge arm clearance that drives everything on a flat deck bridge. But if you've got an arch bridge in particular, you'll end up underreporting clearances. And at some point, somebody's going to notice that. And then you're going to be in a whole world of pain because you've delivered a design that's possibly being built that suddenly has clearances that are below the VCC minimum allowable, and that's all hell's going to break loose on your project at that point. So yeah, but yeah, you're certainly not going to get optimal outcomes if you continue with the traditional approach. I do want to stress though, if you're doing open route cross sections and you're putting pan envelopes on those cross sections, please feel free to continue to use the traditional approach. That's what we're doing in Atkins. We're not developing a pan gauge for every single stovepipe, every single OLE portal, for instance. That isn't necessary. It's horses for courses.
Thank you. Okay, Miguel, you had a question. Are you still here? Would you like to come off mute and ask Gary?
Hi, Miguel.
Hi, Simon. You were talking about the encroachment. So I remember that the standard's fixed to 60 maximum millimeters, the encroachment. Does it mean that based on your tool, the maximum staggers in areas is to be 200 maximum at both sides? Or do we need to change the standard?
I think you mean 60 millimeters maximum, don't you, Miguel? You've put that in your question in the chat. Yes, you're absolutely right, Miguel. Just for those of you who aren't aware, I think it's in 2173. It's in one of the group standards. Specifies a maximum encroachment of 60 millimeters. Interestingly, if you take the Panograph data that's in EPTAN 002 and you apply appropriate contact forces, what you very quickly see is that the Brecknell-Willis pantographs do not stop at 60 millimeters. They do not handily stop out at 60. In fact, let's do a quick live demo, and I'll
This is why my question, does it mean that the standard needs to be reviewed?
Short answer is yes, Miguel, it does. So what I'm going to do now is I'm going to go a bit crazy. I'm going to bang it up to a 350 stagger. Now I know as our PE on Midland Mainline, Miguel, you would never accept a design with this stagger at a bridge, but let's just pretend for a moment that you would. You can already see we have here 140 millimeters of encroachment. I should add, by the way, that encroachment is not simply down to pan head roll. There is another element which is to do with carbon wear. But for this scenario, what I've deliberately done is I've set the carbon wear to 0. So I wouldn't do that in reality. We wouldn't do that on a real scenario. But just to keep things simple here, I've set the carbon wear to 0. And you can see we've got 140 millimeters of encroachment. Now, that's not my opinion, right? That's not the opinion of Excel or Atkins. That's what the data in EPTAN 002 tells us. If you apply a contact, in fact, if I were to do something really silly, like bang the contact force up to 250 newtons, which is as you know, Miguel, is a valid contact force.
Exactly.
Now we're at 159 millimeters of encroachment. So what we have in actual fact, well, there's a couple of possibilities. One is that the data in EPTAN 002 is wrong, but I don't believe that's the case because I know it came straight from Brecknell-Willis and they know what they're doing, right? They know what they're doing. They know how the pantographs work. The other alternative is actually that we have thousands of pantographs on the network that don't comply with the current standard. And in that scenario, it's certainly not the pantographs that need to change. Pantographs are out there doing their job, working fine day in, day out, and we're not going to change them. So yes, the standard will need to be changed. I'm really glad this is a great question, Miguel. Thank you for raising it. Because it gives me a chance to advertise the fact that GLRT 1210, which those of you from electrification persuasion will know is our key group standard, is currently out. There's a new version out for consultation. Version 3 has been drafted and is out for consultation. And for those of you who haven't responded to that consultation, you now have 2 days left. The consultation close of play on Friday. So if you haven't responded to that consultation, I would implore you to. We've all got opinions on 1210. Nobody likes the current version of 1210. I don't think that's an exaggeration to say. Hopefully the new version is an improvement. But you know, if you want to have your say, now is your chance, and you've only got 48 hours. But the consultation version that's out for draft does not specify a maximum encroachment, and indeed actually captures it as an open point that has yet to be fully defined. So we've taken that first step towards redefining encroachment. We've said it's an open point. It would have been nice to have got something into 1210 that said what it should be, but RSSB haven't yet done the work necessary for us to define that properly. So yeah, but the short answer is yes, the standard needs to be updated.
The second part is my last question, I promise. So based on this encroachment, if we are in a curve with a very straight radius, probably it's more effective to reconstruct or rebuild or jack the bridge rather than doing a track lower, because of the encroachment you are proposing. Well, you are showing. Sorry.
Well, the decision on whether you do a track lower or a rebuild, it's not. Encroachment is one of the factors that would play into that. The two things that really affect it are sway and stagger. So yes, obviously on a curve you're going to tend to want to put some stagger on, and that's going to create some encroachment. On the other hand, let's pretend for a moment that this gauge is on it's on a curve to the left. So we've got a left-hand curve. So what I'm going to do is I would typically put it out to maybe, I don't know, let's go to 150 right, say. That would be a fairly typical scenario for a left-hand curve. At the moment, we've got 68 millimeters of encroachment. So yeah, we've got a bit of encroachment, but it depends where the bridge is. If the arch of the bridge was coming down on the right hand side, actually it helps us because it's pushing that end of the pantograph down. So it's pushing that end of the pantograph away from the bridge. If the bridge was over here on the left, then you've got a problem. So let me just I'll do a quick. If the bridge was over here, then it's not good. If the bridge was over here, then it actually potentially helps. It just depends on the scenario.
Okay, thank you very much.
Thanks, Miguel. Great questions.
Thanks, Miguel. Moving on to Robin, you've got a question for Garry.
Thank you, Simon. Hi, Garry, track engineer here. So if I've not quite grasped something, be gentle.
No problem.
I think I'm inferring from what you're saying that if we gauge floating pantographs correctly, we need, in some circumstances, we may need more physical clearance.
That's correct. Yes.
Lower track versus a structure, or larger sleeves versus
or higher,
a structure.
or yeah, we need more space between the roof of the train and the bridge in some scenarios. I mean, let me just do a quick reset. Let me reset the stagger on this. If this was a flat deck bridge, so I shouldn't have deleted those lines, should I? If this was a flat deck bridge, what you can see immediately is that the governing clearance isn't the pantograph, it's the bridge arm itself, which is obviously, it is live. Sure. It has a coated head, so it has a certain amount of insulation on the head, but we still treat it as a live part. So for a flat deck bridge, you're probably okay. It's probably all right. Probably not. Doesn't matter if you fail to consider encroachment. But if you've got if the bridge has my golden rule is at the moment the bridge has got a shape, you need to be worrying about this. So it might be that certain shapes are okay, but if it's got a shape, just start addressing it.
So my question is, do the benefits of the floating pantograph outweigh the potential reduction of capability of parts of the infrastructure?
Yeah, great. That's a great question. Well, Simon has been involved in commissioning Midland Main Line and doing all the high-speed testing there, and also on Great Western, and I had some involvement with the Great Western testing. And what we both see when we're on those trains looking at contact forces is that the only way to keep those contact forces, if you've got one pantograph in the air on a train, the old fixed frames will work fine. They'll work and they'll provide compliant contact forces. The moment you raise a second pantograph, or indeed a third pantograph, fixed frame pantographs don't work. We simply don't run multiple units. We don't run multiple pantographs in the air with fixed frames. If we tried, it wouldn't just be that we broke, because I'm sort of waiting for somebody to say, well, we don't, who cares about the TSIs anyway, which is a whole nother debate we could have. But even if we didn't care about the TSIs, we'd still see contact forces which were starting to get into the territory of potentially causing damage to overhead line. We'd see contact forces of 350, 400, 450 newtons, and these are numbers that make overhead line engineers very uncomfortable, because we're getting, at best case scenario, you're getting increased wear on the contact wire, and over time that tends to lead to further problems, and it becomes a bit of a vicious cycle, and eventually all hell breaks loose, and we get the scenario we had just the week before last, where Paddington Station was shut for a day and a half because the overhead line had been pulled down. So we need floating head pantographs for other reasons.
Okay, we just need to gauge them properly.
We need to gauge them properly, absolutely. Yeah.
Thank you.
If you look at the different floating head pantographs, the HSX Mark II, HSX compared to the HSP Mark II, the HSX performs far better again on top of it. So they are,
which is weird because
a generational change again.
Which is weird because the data that we've been given in ECTAN 002 what I'll do now is I'll switch those two. So these are now two floating head pantographs. On paper, they work almost identically. They have very different springing arrangements. But if I start applying head roll and encroachment, you'll see that they follow each other very closely. So on paper, they're supposed to be very, very similar in their dynamic characteristic. But as you say, Simon, in reality, they don't. I suspect that's down to friction and the hysteresis. I'm sure if we got Nick, maybe we should get Nicholas on one of these sessions.
Or maybe not. We've only got an hour and a half, Gary.
True. But yeah. So yeah.
Right. And then the next question was coming in from Jack Fisher, I believe. Jack,
Hi, Gary. Hi, everyone.
Hi,
Yeah, sorry for the short question there. Just to confirm, so with 0 design stagger, then does that mean that's 0 encroachment?
No, it doesn't.
Or does it start at 20 mil?
Let me just explain that. So
yeah.
when the Panograph is directly under the wire, then you'll get 0 encroachment because the wire's pushing on the center of the head, the springs compress equally, you get no encroachment. The problem is as soon as that vehicle starts to sway left and right, as far as the Panograph's concerned, it isn't 0 stagger anymore. It's actually, so if we look here, so I've set up a 0 stagger, the left swayed pantograph thinks that the stagger is 258 right. As far as the head's concerned, it's got 258 millimeters of stagger on the right hand side. So what that means is you'll get 28 millimeters of encroachment.
So it's still giving a 28. Okay, thanks for that.
So it's the sway that sway element that creates encroachment. And then you also have to consider carbon wear. So what I'm going to do now is add 14 millimeters of carbon wear, and that will also be added to the encroachment. I won't get into the, we make a quite silly assumption when we look at carbon wear, but on the other hand, it's a silly but sensible assumption. So we basically assume that wherever the contact wire is, it's fully worn, and everywhere else it's fully unworn, which is unlikely in reality, but it's a safe assumption. So once you add 40 millimeters of carbon wear, that bumps it up to 42 millimeters of encroachment. And basically, the more carbon wear you add, the more encroachment you're going to get as well. So.
Moving on then, I've got a question from Paul Palmer. If you'd like to come off mute and ask a question.
Hi, Gary.
Hi, Paul.
The question I've got is, we're talking about pan mode here. What the main factors are, as in, is the train velocity one of the dependent factors for pan load? And therefore, are we maybe missing a trick where we're on lower speed lines? We can possibly reduce that pan load to actually get better clearances.
So it's another great question. And the answer is yes and no, and it varies and it's complicated. I'll try and break it down a little bit. So the industry makes a number of approximations when doing pan gauging. The first one is in the sway build-up. So let's go and have a look at the sway. So the sway calculation is a defined calculation based on defined tables, which are in a group standard. So basically, we put in the line speed. So there is an element of speed that goes into the sway, but only in terms of calculating cant deficiency. So basically, we do this is funny because this is actually a track engineer's calculation, and we've just had to, as OLE engineers, we've had to learn to do it, how to do it. So we do a cant, we work out, obviously we know what the actual cant is, work out the equilibrium cant, and therefore work out cant deficiency. But once we've done that, once we've got a cant deficiency, we then calculate the sway independent of speed of the train. All right. So it is related to line speed of the route and the location, but it's not related to the actual speed of the train. And to be fair, the reason for that is we have to gauge for the worst case scenario. So even if lots of our trains are going slower than line speed, we still have to cater for the train that's actually doing line speed. But the other key area is uplift and contour. And this is probably the biggest weakness of this tool at the moment, is that and I'm going to put this back to 150 newtons now. We've assumed we've assumed a contact force of 150 newtons, even though we know that it changes moment to moment between 0 and 300. We've also assumed a value of uplift, which is this 44 millimeters over here. An uplift is a function, well, I was about to say uplift is a function of speed, but we're not sure about that anymore. Atkins, we did a piece of work over the last couple of years where we went out and measured uplifts at various speeds. We didn't see a direct relationship between speed and uplift. That might be because we didn't get enough data. or it might be because it's not actually the dominant factor. Other factors that dominate in play. So there might be, we might be missing a trick in some scenarios, but we really don't, at the moment, we don't have either the data or the tools to allow us to determine that accurately. It's something I'd like for us to, as an industry, to do more work on, I think.
Yeah, I think I'm just very conscious that, you know, obviously there's lots of branch lines that we're going to be looking to electrify, and a lot of those branch lines are traditionally, you know, have traditionally low bridges because they're very old.
Yeah.
You know, they're generally old lines. So if we are, you know, using.
To be fair, I mean, if I were to change, and maybe if you're a track engineer, maybe they'll be out. If we change this to 40 miles an hour, I don't know what a sensible track radius would be on a 40-mile-an-hour line. Let's say 2,000 meters, and I don't know. Again, equilibrium count would be 20. I apologise to every track engineer on this call now. What you're seeing in real time is that I'm definitely not a track designer. So let's put that in at 50 millimeters. You can see that we're allowing. That would mean we would allow 150 odd millimeters of sway, which is 6 inches. Which, not being a vehicle expert either, it doesn't feel like an outrageous amount of sway. We used to use, by the way, back in the day, we used to use a sway value of 230 millimeters. So we have actually the group standard does allow us to reduce the sway as on lower speed lines. Whether those sway values, the thing about the groups, the thing about the sway values that we use, and I'll show you what they are here. So here they are. They're in 2173. These are the tables in 2173. These are published. There's no secret about this. These are the values that we use. They are actually designed for train manufacturers. So the idea is that the train manufacturer has to make sure that his vehicle doesn't sway any more than this value. Should we have a separate set of sway tables for infrastructure design? Is a good question, and maybe we should. And maybe we should do a bit more work on that. So yeah, it's an interesting area. I don't have the complete answer to that question, and I'm not afraid to say so.
Okay, thanks.
Thank you, Paul. Miguel, you've asked, is the presentation available for review? This video will be uploaded onto the PWI website in due course, once Sarah gets hold of Gary's presentation and video. So hopefully that answers your question. Moving on to Keith Worski, you've got a question there?
Yeah, thanks, Simon. Thanks, Gary. Great presentation there. How you doing? Yeah, appreciate you're looking at predominantly clearances to, well, overland clearances to bridges and whatnot, but with the floating head essentially rolling cross track like that, you'll also get reduced clearances to the train. And the minimum wire height in the new GLRT 1210 is 4040.
It is, and I'm really glad to see you've been reading the consultation version. That's great.
So I'm just surely, if with the rotating head, the clearances to the train will reduce.
So let me explain why that I don't think that is the case, and I'm just gonna. I tell you what I'm going to do. I'll bring up. I think the best way to show that is to bring up the EPTAN itself. So this is where all. If you want to know where the data that underlies this tool comes from, it's all in here. So I'm going to zoom in on this. So this is one of the floating head panographs. Hopefully you can see this. That makes sense.
Yeah.
See that okay?
Yeah, I can see the drawing. I presume Keith can.
So the horn here is fixed. That's not going to move. The part that moves is this part here that's got, if you look at the part that H is pointing to, and there's the spring there, that part's going to move. So it is certainly true that as this spring compresses, the bottom of this point will move closer to the train. However, the train manufacturer is responsible for ensuring that electrical clearances between the live parts of the pantograph and the earth parts of the vehicle body, that those clearances are always greater than the minimum allowable. The train manufacturers and Brecknell Willis, in fact, have been consulted during the development of the new version of 1210. So Brecknell Willis have been consulted. Train manufacturer, in fact, there is a representative for train manufacturers who sits on the Energy Standards Committee that have been looking after the development of 1210, and they are all comfortable that those minimum clearances will be maintained even with a wire height of 4040. I should add that having a wire height of 4040 under all conditions is not something new on the UK network. We already have, in fact, so Network Rail did some analysis and they found that they had, I can't remember, that it was some crazy number, that we have kilometers and kilometers of route on the network already with wire heights below 4165. There are places on the network where we do have wire heights as low as 4040 already. So the short answer is we're comfortable that the clearances between the pan and the vehicle will be maintained. And certainly the clearance between the contact wire and the vehicle, a minimum of 75 millimeters, will be maintained with 4040.
Okay, great. Sorry, my Wi-Fi cut out for half of that explanation.
Oh,
but
apologies.
I'll rewatch that. But yeah, thank you.
I think it did answer your question from my perspective, Keith.
Okay.
So please rewatch. Okay. Okay, Mosmalali, you had a question regarding the pantograph uplift and the reality. I think Gary's covered that in some of his previous answer with the recording and measurement of it, but needing to go and do further analysis and testing. And so I think we're currently reverting back to what the system design has been allowed for. Is that correct, Gary?
Essentially, yes.
Yeah.
So the EPTAN specifies a value of 43 millimeters for elastic bridge arms, and that's based on some work that Atkins did a couple of years ago. If you haven't got an elastic bridge arm, then you need to use the free running uplift, as you say, Simon, from the system manuals. That's an area that we're also looking into. I think in future we're being asked to do some uplift monitoring for open route as well, which the intent of that work would be to refine those system values, but at the moment stick to those system manuals.
Yeah, right, great. Sorry, Mosmo. And then there also Rajesh, you had a query regarding as it is changing the clearance between bridge arm and panto, do we require to change the position of the bridge arm?
Great question. Short answer, yes. In fact, we've built that facility into this tool. Let me just think about. We need to set up a scenario that allows that to happen. So the way to read this, I think what I'll do, I better do first of all, is just switch off the static bridge arm, because that's just going to confuse everybody. So let me just deliberately switch that one off. Right, here we go. So this is again, VCC. We've got a bridge arm at 0 stagger. As soon as we start, let's say we push that stagger out to 200 millimeters. No, let's go the other way. Let's go the other way. Let's say we push the bridge arm out to 200 millimeters that way. Bear in mind, the bridge arm is considered a live part and the panograph is considered a live part. So you don't need an electrical clearance between the two, but you sure as hell do need a mechanical clearance between the two. So what we can see now is that this swept envelope of the panograph is getting very, very close to this bridge arm, too close for comfort. So what we can do then is we can start rotating the bridge arm upwards, put say 4 degrees of rotation. Remember, this is an exaggerated view. It wouldn't look like that. In reality, it would look like this over here. Then we can put an angle on the bridge arm. And I think traditionally overhead line engineers haven't specified that angle. We've kind of left it to the installer to work it out. I think at tight bridges like this one in future, we'll probably find ourselves needing to specify an angle, because in reality for the installer, it's very, the installers aren't wandering around with a floating head pantograph in their back pockets checking gauging. It's quite difficult to check gauging at speed. So I do think that we will probably need to specify the angle. Hopefully that.
Thanks, Garry. So does it change the clearances between the bridges of it and also the live part, because we are changing the angle?
Yes, it will. Absolutely. Absolutely.
Yeah.
One other thing that I think designers aren't aware of, you'll notice that I'm deliberately going to put a 200mm clearance on the bridge arm a minute. So let's get rid of VCC for a minute, go back to the old school way. So just deliberately exaggerate. You can see here, so we've got 200mm clearance envelope around the head, but you'll notice I'm dropping down here to only 10mm of clearance on the back of the arm. You're allowed to do that. You're allowed, 50119 allows you to have 10mm clearance at the earthed end of an insulator. And I think that becomes really important with these sorts of bridges, because if I change that back to, traditionally we would have just put, and even, you know, in Atkins we're no different. Traditionally we would have changed that to, that's interesting. Bear with me, I'm just going to go unprotect this sheet so I can change that one. So if I were to change that to 200, go back to chart, you can see the effect of that now. So suddenly you've got a real problem at the back end of the arm because the bridge might be in the way. So yes, OLE designers use that 10mm value. It's in 50119, it's in EPTAN 002. Oh no, changed the wrong one, that's why. It should be that one there. Use it. It's there to be used, and it gives advantage when you've got an inclined bridge arm like this. And it's not just when you've got a high stagger situation. I mean, this is a pretty weird setup. You probably wouldn't design a bridge arm like this in reality. But what if you've got heavily canted track? Remember, everything here is drawn in the plane of the track, right? So if you've got heavily canted track, then your bridge arm is going to be inclined, even if it's level with the plane of the track. It's going to be inclined to gravity, and this 10mm can give you a benefit. So use it.
Thanks, Garry.
Thank you, Garry. Sorry, Mesmel and Rajesh, I hope that's answered your questions. I'm just very conscious of time, and we have overrun a little bit. So if I can, I'll do the normal, ask everyone to show their appreciation to Garry for his excellent presentation. I think we've peaked at over 100 people participating, which I think is a great number for West of England section. So well done, Garry.
I just
thank
interject and I've just seen David Johnson. If that's David Johnson from D-Gauge, I'd just like to apologise for everybody at D-Gauge for my incredibly crude description of gauging, but it's good enough for a simple engineer like me.
Great. Thank you very much, Garry, and thank you very much, everyone else, and hope to see you for our next section meeting.